typically 0, right? Yeah. Ions, on the other hand, are going to have an uneven number of electrons and protons, right? Specifically, we've either gained or lost electrons. And so ions are going to have positive or negative charges, aren't they? Okay. Now, the number of ions that can be combined to form an ionic compound, this is going to be determined by the charge of the cation and the charge of the anion, because you're going to have to balance these out, right? Kind of like your checkbook. Remember that really this is just accounting. Okay, it's accounting for electrons. Right? You go into a store, you need to pay $5 for something. How many dollars do you need to give until you get it? $5 or a $5 bill, right? Okay. And so we're going to do the same sort of thing to balance these out. Has anybody ever done cross multiplication before? Okay, so like let's say I want to take and add a 1/2 and a 1/3. How do I do that? Yeah, cross multiplication, right? I'm going to take the 3, I'm going to multiply it by the 1/2, right? And then I'm going to take the 1/3, and I'm going to multiply that one by 2, right? So they'll both end up with 6 in the denominator, okay? We're going to do something that's the exact same concept, okay? So the cations and anions, they have to combine so your compound has a net charge of 0. If you had something that had a positive or negative charge, it would be unstable, and that would be theoretically not possible, okay? It is actually something that can be done and is done in the real world, but it's very unusual and it's an unstable state, right? Okay. When writing formulas for chemical compounds, we can represent the number of each particle in the compound with a subscript. Remember the same thing as like H2O, right? We use a subscript to tell us how many of them there are, right? Now, keep in mind, you do have to be a little bit cautious about this because we have things like polyatomic compounds, right? We have things like polyatomic anions, okay? And so you have to make sure you use a parentheses if it's something you have to keep together and multiply as a set, okay? So, common place to make mistakes. The charges in the formula of an ionic compound are not normally shown because you're going to balance them, right? So you've actually provided all that information in the balancing act. Okay? Okay, let's go ahead and do it, because that's usually the best way to learn. Step 1, we determine the charge of the ions from the periodic table. If they're main group elements, that's going to be really easy. So we look at our periodic table, we notice that oxygen is how many steps from a noble? It wants to take 2 steps to the right. And so its charge, its preferred charge is -2, right? How about fluorine? It's 1 step from a noble, that would be a -1 charge, right? Okay. Aluminum, on the other hand, if we look at that, it's on that 3rd group. And what we notice is that it's closest to the left side of the periodic table, isn't it? Okay. And so its preferred charge is going to be 3 steps to the left to go up a period to be like that noble gas, right? Okay. That making sense for everybody? Okay. Please do take out your periodic tables any time, because I just can't fit periodic tables on all my slides, right? And there's no periodic table in the room. So you'll probably want to have a periodic table during the lecture, okay? It's just not something I can, like, deal with here. I'd have to double all my slideshows, because I'd had periodic tables back and forth every time, right? Okay, now this right here is actually combining these together. Okay, so has anybody ever seen aluminum before? Like aluminum foil, aluminum cans, right? Okay, did you know aircraft are made out of aluminum alloys? Right? Do you know what you're not allowed to bring on an aircraft besides a bomb? Huh? Yeah, you can't bring certain types of batteries. One of the big ones is mercury. Okay? You didn't know that, did you? But if you look at the sign as you go on, you'll see right on the front, it lists mercury. It's the oldest one that has been banned from aircraft. The reason for that is mercury is a liquid. If you were to spill mercury on a plane, what it would do is it would actually rapidly corrode through the hull of the plane, putting a hole in it. Okay? It's not so rapid that it's like plunk and then whoosh. Right? It'd be more like plunk and then the next flight a few days later, depressurize and then possibly get destroyed. And so this is because aluminum is super reactive, actually. Has anybody ever scratched their aluminum cans or aluminum anything? It's like really shiny, right? The metal's super shiny. But when it rapidly dulls within like 10 seconds, did you notice that? And it becomes like this dull gray color. And so that dull gray color is aluminum oxide right here. That's the rusted form of aluminum. Okay? It's very hard and very resistant to corrosion. And so it actually protects the aluminum. Right? If you spill mercury on a plane, it actually dissolves this aluminum oxide. And then you end up just corroding the aluminum continuously. And so it just corrodes continuously, and it ends up with a hole in it. Yeah. And it ends up a pretty wide hole, actually, surprisingly so. Kind of like if you had left a plane in a plane yard, dead plane yard for like 50 years. Okay. Anyways, how we balance this is, look at this. We have a 3+ charge. We have a 2- charge. How in the world do we balance those charges? Can we just put one of each? And that would leave us with a positive charge, wouldn't it? Okay? If we had a whole charge, it would have to go up here for the whole thing, right? This not having anything there tells us the charge is 0. Okay? And it needs to be 0 overall because that would be unstable without it being 0. Okay? Okay, so how do we always balance something where it's an odd and even, you want it to balance out? Well, the easy way is always to take the odd number and the even number and multiply each other, right? And that's the easiest way. Okay? And so we take 3 and 2. What we do is we cross the 2 for the aluminum and the 3 for the oxygen. Can everybody see that? It's just cross multiplication, isn't it? Same as you would have done back in elementary school for fractions. Okay? Okay, is everybody comfortable with this? Did I lose anybody? No? See the subscripts? Those are the numbers of things. Okay. Question or just stretch?
Question.
Okay.
So, how do you figure out the charge of the ion? I'm sorry, I wasn't here last week. So.
Okay, so what you want to do is you want to look at your periodic table.
Mm-hmm.
Okay, so on your periodic table, everything wants to be like a noble. So see the noble gases, which is column 8, group 8, on the far right.
Okay.
Okay. You okay with that?
Mm-hmm.
Okay. Okay, so the stuff on the right side of the periodic table typically goes right. The number of steps it is from the number of elements to the noble gases. And so, for example, oxygen is 2 steps from a noble, right? And we're going right, so we gain electrons. So oxygen always ends up with a 2- charge. Fluorine, 1 step from a noble, right? And so that ends up -1 charges. We look at carbon, we see that's 4 steps, right? So that typically ends up with a -4 charge. But this is where things get a little interesting. Try going left on the periodic table and counting over that way. So if you look at carbon and you try going left, you notice you'd fall off after 4 steps, right? That means you would go up a period. And so carbon can actually be -4 or +4. Okay? It can either gain 4 electrons to be like the noble gas on the right, or it can lose 4 electrons to be like the noble gas on the left. Okay. Once we get over to aluminum, see aluminum Al? Okay. That's 3 steps to the left is actually your closest way to get to the next noble gas. So if you go left from aluminum, 3 steps, there's not elements in those. So skip the middle part where there's no elements. Aluminum. 1, 2, 3. It's like noble again. Is that making sense?
No.
So there's nothing here in the middle.
Right.
Just-
Well, you,
that's it.
like, so for fluorine, you said from 8 it would be -1. Why would it not be -5?
So it'd go to this
from-
one.
Oh, it goes to the right.
Yeah, that would be gaining electrons.
Okay.
Going to the left would be losing electrons.
Mm-hmm.
Okay. So we go here, boron. This is group 3. 1, 2, 3 would make us like helium. And that would be losing electrons. See how the number goes down?
Mm-hmm.
Okay. Does that make more sense?
Yeah, but then why is carbon -4?
It can be either.
Because are you always counting like 1, 2, 3, 4? Oh, okay.
Yeah.
I was
So
I
we
was
can-
counting from 8 and going to the left rather than counting from here and going to the left. I get it.
Ah, okay.
Got
Yeah,
it.
you always go to your element and then count.
To
off
the
there.
left, not from the noble gases to the left. Okay,
Yeah.
got it.
Yeah.
I was doing it
Well,
backwards.
left or right.
Yeah.
So for this one, for example, nitrogen, 1, 2, 3 steps to the right, and
Mhm.
so that's going to be a -3
Right.
charge. That making more sense?
Yes.
Fantastic. All right. So, everybody go with cross multiplication?
The whole group, the carbon, which is 4A, the whole group, 10 lose and gain 4.
Yes.
Like the 10 is a methyl, so I think it should only lose
Which one are you talking about?
the lead.
I'm sorry.
The lead.
Lead?
Yeah.
So we're going to be carefully sort of working around the stuff lower on the periodic table. And so carbon's group, you can always go left or right. Once you get very far down, what ends up happening is you tend to go left a lot more. And there's actually an effect that allows you to have multiple different charges. So once we get down to here, if you look on your periodic table, that center block, which is the transition metals, everybody see the center block on your periodic table? Yeah. That center block is transition metals, and after that, you can have everything ends up being metals in the bottom there, and they can have multiple different charges. You could have a 2+, a 3+, like iron. You could have a 4+ and a 6+. You could be like chromium.
Yeah.
Yeah, +3, +6. Okay. And what you end up finding out is everything starts losing electrons much easier. Okay? But the majority of the stuff you all are going to be concerned about and actually have to deal with in life, period, is actually groups 1, 2, and 3. So, yeah. This is this rule works really well for 90% of the situations you would actually deal with in life. Yeah. Now, lead can go the other way.
Yeah.
Yeah, it can go both ways. So, for example, you can get lead where it actually takes on 4 bonds from something. Okay? And so it can still do the carbon stuff. It just tends to do more of the weird stuff where it like loses 6 electrons to things because it's a metal. Yeah. Yeah. And if you're interested in why, actually, I can talk to you, but it's totally out of scope for this course. Yeah. It's actually an inorganic chemistry thing.
Yeah.
Which is funny because I actually just taught that like last week, Thursday.
I wasn't there.
Yeah. No, you won't be. That's 420 for chemistry. No. That'll be way advanced. Okay. So rules predict number and charge in chemical formula. Again, the formula of an ionic compound has no net charge. Your pluses and minus charges have to equal up to 0. You can think this very successfully as basically balancing your electrons, right? Like you'd balance your dollars in your account. Okay? Just remember electrons are negative. The charge of the anion is typically the one we're going to know. It's the one that's the most obvious, the easiest to predict. The metals, yeah, groups 1 and 2 are pretty easy. The transition metals in the middle, not so easy. Okay? And so the metals are usually what you have to add up and figure out from the negative charges. If you know the negative charges, you have to know the positive as well, don't you? Because they have to equal out. Okay? All right, so let's talk a bit about naming ionic compounds. To name an ionic compound, the names of the 2 ions are going to be combined. You'll put the cation first. The word ion is going to be omitted because it's obviously going to end up being an ion. We just don't need to say that. Scientists are lazy. We need to communicate quickly, right? Okay. And so NaCl Na is normally sodium, right? And so that would be sodium ion normally if you're talking about as an ion. In the case of an ionic compound, you just put sodium, okay? Okay. And then we're going to put, for the anion, the ide form. So for example, chlorine in here is going to go to chloride. And so this would then be sodium chloride. This is the part that tells you, hey, I'm ionic. The I. Okay? This part, there's no difference in the metal. Right. So sodium chloride. Everybody good with that? You've probably heard it before quite a few times, haven't you? Table salt, sodium chloride. Yeah. Yeah. Sodium levels are high. I know, right? That was why. Technically, that should have been sodium ion levels are high. If you want to be real pedantic about it, you should totally do that to your doctor. Watch their blood pressure rise. All right. So for transition metals, we actually have to add one extra thing. We have to add a Roman numeral. This is going to be used to tell us what charge it is. And that's because when we get into the transition metals, they don't have just one charge. That's possible. They have multiple charge states that are possible. And so, for example, we look at this, CuO. Notice that that actually tells you what the charge of the copper here is, doesn't it? Because oxygen is what charge? Yeah, 2 minus, isn't it? They're one of each, and so this Cu has to be 2 plus, doesn't it? See that? And so copper, 2 for a 2 plus charge, Roman numeral 2. And then oxide, because this is the charged anionic form of oxygen, right? Okay. So see how there's lots of information packed in there, isn't there? To make it real convenient to figure out. All right. So if a polyatomic ion is present, the name of the ion is going to remain unchanged in the name of the compound. For example, right here, we're going to have calcium phosphate. Remember, the polyatomic ions are already ions, right? So their names already tell us they're ions. We don't have to do anything to indicate that they're ions. So right here we have Ca3, parentheses. See, the parentheses are very important. Putting a 2 right next to the 4 would not be the same thing, is it? Putting a P2O8 is, again, not the same thing, is it? Okay? And so PO4, 2 of them, parentheses. Okay? Okay. Can everybody understand that those are very, very, very different concepts, right? Kind of like me saying that a human, 2 humans has 4 arms. A single body with 4 arms on it would not be 2 humans, would it? Okay. That'd be a whole different thing. Different genre, in fact. Okay. And so, is everybody okay with calcium phosphate so far? Huh? Okay, fantastic. All right, so nonmetals are going to be combined by sharing valence electrons to achieve an octet. Remember that octet was the book's way of saying a noble-like configuration. Okay? Okay. Are you guys okay with octet being noble-like configuration? Okay. Yeah, everybody understands why I'm stressing that, because like hydrogen never gets an octet, right? Never gets 8, but it fills its octet. Absolutely hate that terminology, but your book uses it everywhere. So
Octet means 8 electrons in the outer valence shell, right?
yes, it does.
Okay.
Yeah, yeah. So its outer shell has 8, which is the noble-like configuration. For the majority of cases, you're going to deal with. But in reality, what that means is just noble-like configuration. So it has a configuration like noble gases. Okay. All right, so the sharing of electrons is going to result in the formation of a covalent bond. Covalent bonds are going to be where you share electrons evenly between 2 atoms. That sharing of electrons is going to pull them together and hold them together. Notice ionic bonds, you did not share electrons, did you? Okay? One of them took it from the other. They were held together because you have a positively charged sphere and a negatively charged field, and they're attracted to each other, right? Covalent bonds, on the other hand, are typically not charged, and they're going to have the electrons being held in between and shared between. Because they're both pulling on those electrons, you're going to end up bonded together and staying together, right? Kind of like if you both want to keep a pencil, you end up attached, don't you? Okay. Okay, so the valence electrons in your bond is going to belong to both atoms, and so we count their attributions to both to a degree. Okay? They count towards having full of valence shells because now they're sharing. All right. And so when atoms share, the result is going to be what's called a covalent compound. Okay? And so this is things like water. Water is a covalent compound, or things like methane. Notice that those are not ionic compounds. You didn't know them as salts, right? Okay, so those were covalent compounds. The smallest or fundamental unit of a covalent compound is going to be called a molecule. Okay, and this is where molecules have come in. Everybody had probably heard of those before, right? And so molecules are going to be covalent compounds. They're going to be single units of those. Now, remember how we had just talked about ionic compounds? Ionic compounds actually don't have molecules. Okay? They're actually just repeat units of the same thing over and over and over. You can't actually identify a single one of those units as being it. Right? Has anybody ever seen a molecule with their eyes? No? Who thinks you've seen a molecule with your eyes? Nobody? You? No? Nobody wants to commit to that one? Who here thinks you have not seen molecules with your eyes? Come on, be a little brave. Commit to something. Okay, so the majority of people are willing to try to play with me. Okay, you interestingly enough, there is an example of a molecule you can see with your eyes, and it's in this room right now with you. Okay? See this stuff on your head? Okay, those are polymers, and they're very long, and so individual hairs are actually single molecules. I know. And you can also see things like your DNA, if anybody's done that DNA extraction with strawberries when you were a kid. Yeah. So there are examples of single polymer molecules that are just really big. Okay? So let's talk a bit more about naming ionic compounds. The number of covalent bonds that an atom will form is going to equal the number of electrons that are necessary to complete its octet. So let's go back to oxygen, our trusty oxygen, right? How many electrons does it normally want to gain? It's 2 steps from a noble, so 2, right? Okay. So oxygen is going to typically make 2 bonds to fulfill that requirement to gain 2 electrons. So instead of taking 2 electrons from something, it instead is going to share, so it gets those 2 extra electrons. Okay? Kind of like you might have done if you want to like watch a streaming service or something, right? You share your streaming service, the other person shares the other. And then the streaming service is very angry with you. All right. So we're going to have electron dot symbols. These are going to be developed by chemists G and Lewis. This is actually going to show how atoms share electrons in covalent bonding. A lot of you have actually probably seen these before because they're a fairly popular thing to show people in like middle school or high school level sciences. Okay. These are called electron dot symbols for any atom that consists of an elemental symbol, and then they're going to have dots, and those are going to count up to give you your valence shells. Okay. And what you do is you typically put 1 dot on each side of it. There's 4 sides, right? Until you have to double up because you have more than 4. And then you'll start doubling up. Okay, let's look at. So here we see an electron dot symbol for chlorine. Can everybody see that okay? See it has a chlorine there. Cl in the middle. And then we have group 7, right? And so this has 7 valence electrons. Okay. So we filled in 7 electrons around it. That's 3 sets of 2, 1 that doesn't have a set, right? It's not paired. Okay. And so if we put a bunch of chlorine atoms together into a flask, what we would end up seeing is those chlorines would join together and they'd form Cl2. Okay? And that's because each of the chlorines can share one electron to make a bond. That bond allows them to have a set of 8 electrons around each. Can everybody see that okay? And so now they're noble-like, aren't they? And it doesn't require one of the chlorines to somehow take the electron from the other, because now they're sharing. Okay, so this right here is how you represent that covalent bond. Okay? You put a line in between. This would be another way to represent the covalent bond, and that's putting 2 dots in between. They're the same thing. For you all, please do not try to write, when you're writing on paper, this type. Okay? If you try to write 2 dots in between, what you're going to find is you oftentimes don't press hard enough, or sort of press in a way that your dots actually can be seen later. And what will happen is you'll be talking to me about your notes and going, none of this makes any sense. And it's because you have like one dot you can see, and then the other dot is like way over here, or you can't see it. It looks like a grain in the paper. All right? And you'll go back in your own notes, and nothing will make sense, and it'll all be a pain in the butt. And yeah, it'll just be a giant disaster. Okay? It's like 70% of students, if they try this method of writing them out, it's just going to be a huge disaster for them. Okay? This method right here, the line, well, you have to commit to a line to make it, don't you? And so typically this method works very well. Okay? And so you put a line for a bond. How many electrons would be in that line, that bond? 2 electrons. So anytime you see that covalent bond, that line, that's going to be 2 electrons. They're being shared, aren't they? Okay. Okay, anybody have any questions about those so far? All right, these right here, notice there's pairs of electrons that are not being shared. Those are called lone pairs, right? They're not going to be shared with any other atom. They're just hanging out by themselves. Okay. All right. So let's talk about finding your octet and getting your octet. So we're going to ignore carbon for a moment because it's in that weird area that's the 4, right? So we're going to commit to the easier ones first. And so if we look at oxygen, we see that we would be 2 steps from a noble, right? And so oxygen has 2 unpaired electrons. It's going to try to make 2 bonds with stuff. Okay? If it can't take the electrons wholesale, it's going to share its electrons twice to make 2 bonds. Notice this is the exact same pattern as we had seen when we were talking about steps to a noble, right? Yeah. How about fluorine? How many bonds is that going to want to make? Just 1. Yep. And so the stuff in that group wants to make how many bonds?
1.
Yeah, 1. Chlorine, bromine, iodine, they all want to make 1, right? Okay. Oxygen, same thing. Sulfur tends to make 1 bond, right? Or 2 bonds, excuse me. If we look at nitrogen, how many bonds does that normally want to make? 3, exactly. 3 steps to a noble, or another way of thinking about it, 3 unpaired electrons, right? 3 slots to make bonds. Okay. Hydrogen, how many bonds does that typically want to make? Yeah, just 1. Yeah. And that's because if it gets 1 more electron, it has its full noble-like configuration. There's only 2 elements on that period, right? Yeah. Okay. Everybody good with that so far? Okay, fantastic. Now, carbon is a little bit interesting. It can do a lot of cool stuff. And that's actually why, do you know what we're made out of? Carbon. Yeah. Yeah. We're made out of carbon. That's the base molecule everything's made out of, right? In terms of life, organic compounds, all that, right? And the reason for that is that it can do some really, really cool, crazy chemistry. Okay? Now, overall, carbon wants to make 4 bonds. Okay? That's still true for carbon. But you can get some derivations from that, a little bit of wiggle room from it, right? Because remember that carbon's in the middle, isn't it? So if you go right, it wants to gain 4 electrons. If you go left, it actually wants to lose 4 electrons, doesn't it? Okay? So it's in that sort of happy medium place, and what you'll actually see is, for example, it can bind to these other things, and some of this other stuff can start pulling those electrons from it. Okay? All right. So, again, carbon must form 4 covalent bonds to complete its octet. It can form 4 single bonds. It could form a double bond, which would just be 2 bonds to that carbon from the same thing. Okay? Anybody ever heard of like a trans fatty acid? Nobody's heard of trans fatty acids? Okay. Omega fatty acids. Okay. Okay. Both of those have double bonds in them. That's actually what makes them omega or trans fatty acids. Okay. Anybody ever heard of peanut butter? Okay. Do you know how peanut butter is made? Hydrogenation. And so what you're doing is you're actually breaking the double bonds on the peanut oil, and it makes it so it melts at a higher temperature. And so normally peanut oil would be a liquid at room temperature. You break those bonds, all single bonds, no double bond, and suddenly it starts melting at a higher temperature like toast. Okay? There you go. That's peanut butter. So again, double bonds sharing 2 electrons with one other atom, or another way of saying that is each bond has 2 electrons in it, right? And so there's 2 bonds, 4 electrons total from all the atoms included. So a triple bond would be making 3 bonds to a single other atom. For example, another carbon, we would have 3 bonds in between. This right here is a triple bond. These are examples of double bonds. Here we have 2 double bonds, 1 double bond, and these are right here are single bonds, right? Okay. Everybody good with that so far? Fantastic. Okay, keep in mind again, why are we doing this? So that we can have an electron configuration like a noble gas, right? Or an octet. Okay. Okay, so this right here is again going to be the normal bonding patterns for each of these groups. Notice that carbon is more complex because we have a lot more options, right? And so that's why carbon's the backbone of all life. Okay? Nitrogen also has quite a few options, and oxygen has some options. Notice that life is composed of carbon, nitrogen, and oxygen. Huh. Okay. All right, so let's talk about some of the molecular formula. So molecular formula for a covalent compound is going to identify all the components in a molecule. Glucose has a formula of C6H12O6. Does everybody know what glucose is? Okay, it's the sugar that powers your brain, right? Yeah. Do you know that essentially all energy that powers your brain comes from glucose? Yeah, your brain doesn't use anything else, essentially. Okay, and so this right here is the formula for that. Notice it's the number of carbons, number of hydrogens, number of oxygens. Okay, and these are all the elements that are in there, and their numbers. The molecular formulas of covalent compounds do not reduce to the whole number ratio like an ionic compound would. So an ionic compound, if we were to write something like this, like a calcium fluoride, and we put like 3 calcium, 6 fluorides, you divide it by the same number to normalize it. Okay? And so you take that, divide it by 3, right? You get 1 calcium, 2 fluorides. Okay? We don't do that with molecular compounds because they have a singular version of it, which is called a molecule, right? And they're just not repeated units over and over. Okay? So it would be a very different molecule if we were to do that. That would no longer be glucose. In fact, that would be another sugar, in case you're wondering. All the sugars have the same sort of multiples with each other. Okay. So again, we keep that 6, we keep that 12, we keep that 6, right? We don't divide it by 6, so we can get the lowest whole numbers. Okay. The formula does not show your structure. The electron dot symbols help us actually visualize and create those structures. And so what you will actually notice is there's different molecules, there's different compounds that have the same formulas. Okay? And some of you might have encountered that in the reading, hopefully. And those are referred to as isomers, right? They have different structures, but the same formula. Okay, so right here we have methane. This is going to be a molecular formula of CH4. Does anybody recognize methane? Anybody recognize methane from your lives? Yeah, natural gas. Yeah. It's the primary component of natural gas. Okay? Natural gas is actually a mixture that changes depending on where you are. And so it can range from 60-something% up to 90-something% of natural gas. Okay? Depends on where you are. This is a covalent compound. It's all nonmetals. It'll share all those electrons between each other. The carbon must make 4 bonds to complete its octet. And so we'll put the carbon in the middle. We will then join hydrogens as single bonds to that carbon because each hydrogen wants to make how many bonds? 1. Yeah. And so we have carbon in the middle. It's bonded to 4 hydrogens. This would be how you'd write it on your paper, and that's what's called a Lewis structure. Okay? Everybody okay with that so far? And see, it tells us how things are attached, right? That's not all of the information. Notice that we can't really tell what the 3-dimensional structure looks like yet, right? But at least now we know what's attached to what, right? What's sharing electrons with what. So let's go through the steps for drawing a Lewis structure for covalent compounds. Number 1, we draw the correct electron dot symbols. Number 2, we then line up the atoms. Number 3, we draw the Lewis structure. Number 4, we confirm the valence shells are complete. And number 5, we'll check our structure. Let's go ahead and go on to the naming quickly, and then we'll do a little practice eventually with the Lewis structures, making them, okay? Actually writing them out. But let's talk about naming. So naming covalent compounds is a little bit more complex, but that complexity is not bad, okay? It's actually kind of nice because you always kind of know what you're expecting. So binary compounds, these are things with 2 different elements joined together. Okay. These are going to be, again, 2 elements, and we only have 3 steps to the procedure. So you'll name the first element in your formula, you'll name the second element in the formula, and then change the ending to "ide," only for the second element. You'll designate the number of each element present using one of the Greek prefixes, and I'll give you those Greek prefixes in a moment. This is going to tell you the number of each element present. Again, that's important because, again, for nonmetals, covalent compounds, that number changes what compound it is, right? So, for example, water has H2O. Hydrogen peroxide, which you would not want to drink, has H2O2, right? Okay. Those would have different namings, and so we can indicate which one is which by those namings. So some of the compounds like water, H2O, ammonia, NH3, and nitrous oxide, N2O, most people just say their traditional names. Okay? It's very unusual to see them expressed in this correct compound naming. Just nobody wants to use it. So, right, here's the prefixes. Those are the Greek prefixes we were talking about before. So mono, like monocycle, is 1, right? Okay. Di is 2. It's a little bit like bicycle, right? 2. In fact, bi and di have a common origin. In case you want. Tri, like tricycle, is 3. And then 4 would be tetra, like Tetris. 4 sides. Okay. Penta, like pentagon, is 5. Hexa, like hex wrench, is 6. And hepta is 7. Everybody okay with that so far? Okay. So if I have, for example, 2 hydrogens, what would I put before the hydrogen? Di. Okay, I have 1 oxygen. What do I put before the oxygen? Mono. And so if I was to correctly name water using this, it would be dihydrogen monoxide. Okay? there's a really, really funny trick people play when they first sort of learn this naming convention. Okay, so, man, I have the most deadly and most destructive compound on the planet to tell you guys about. Dihydrogen monoxide kills more people per year than every other compound combined. It damages more property than every other cause combined. It causes more damage to the planets and the infrastructure of humanity than any other cause. It has a 100% addiction rate. There is no one that has taken dihydrogen monoxide that can live without it once they've taken it. So what did I just tell you all? Water, right? Water causes more damage than a property than any other cause, right? Duh. We're talking about rainstorms, typhoons, all those, right? Yeah. Water, 100% addiction rate. Anybody here that can go without water? No, you have to have water. You'll die without it, right? Yeah. So, obviously, silly, right? But all true, including the name. And so people play this trick. They actually did this to Arizona State Legislature, and they tried to pass a law outlawing dihydrogen monoxide. And they got to the appropriations level, which is the last step before you'd vote on the bill and implement it. And then finally, the people that were doing this was back in the 80s before internet, but internet has not helped. Okay? Finally, the people that were doing it were like, no, don't do that, because they were going to like spend money to do this. And it's actually hard to get laws off the books once they're on, right? So they would have outlawed water in Arizona. And I actually had somebody do this, like the first couple of years I was teaching. They went on to like Facebook and they were like all joking around with each other. Ha, ha, ha. And people were like falling for it. One of my students' mother actually got so mad at him that he was laughing and joking about this on Facebook, and this is such a terrible compound, how could it be allowed, that she didn't talk to him for 2 weeks. She just wouldn't talk with him. And the funniest part about that is literally you can like double click and right click, right? And you would know what dihydrogen monoxide was. Like, this was such an easy thing to find out that it's just water, right? Yeah. Mm-hmm.
So, like through reading chapter 3, it doesn't look like that the first element, if it's mono, you don't put mono, correct?
No.
Okay.
That's the next thing I was going to get to.
Okay.
So whenever you have the first element, technically you can put mono, okay? Sure. But it's one of those conventions that you really just don't need to. And so you leave the mono off by convention on the first element, okay? So for example, carbon monoxide is a great example of this, right? That's CO, and carbon is the first element, and we don't put the mono, right? Yet we put the mono for the second one. So carbon monoxide. Okay? Carbon dioxide, another good example of that, right? Okay. And ones you've all heard of many, many times. Okay, so before we name any compounds, we always have to determine, is the compound ionic? So a metal with a non-metal. Everybody remembers how to tell the metals, right? Left of the periodic table, left of that stair step, right? Non-metals to the right of the stair step, up and to the right. Okay, if you have a metal with a non-metal, that's going to be ionic. If you have two non-metals together, that is going to be a covalent compound. Okay, everybody okay with that so far? All right, once we figure that out, if it's ionic, the metal in group 1A, 2A, or 3A, then those are easy, okay? Because we can automatically tell what the charges are. We don't have to put any Roman numerals, right? And so no Roman numerals, no Greek prefixes. We just have to put NaCl, okay? Or MgCl2. That's it. Congratulations. If it's not one of these 1A, 2A, or 3A metals, those ones have variable charges. they could have different charges. And so we have to indicate that charge on the metal. And so that's where you're going to use Roman numerals to indicate the charge. And that's going to be things like Fe3Cl3. Okay? That would be with your Roman numerals. If it's a covalent compound, you're going to use Greek prefixes. You don't have to worry about charges at all because we don't have charges. You just have to worry about balancing out the bonds. So you'll use Greek prefixes, and those will be the mono, di, tri, etc. Okay. All right, come on. There you go. Chemists, we have to work in larger amounts than molecules. We can't usually take an atom or a molecule, put it on something, or even manipulate those individually, right? They're incredibly small, okay? And so what ends up happening is we use a unit here that's like saying package of, okay? So you know how you buy like ramen, right? Do you buy one ramen noodle? No, you buy a package of it, right? Okay. And so that's what moles is going to be like. It's packages of atoms. It's packages of molecules, okay? And it's an amount that we can actually manipulate and work with in lab. So it's going to relate to the mass of an element in grams. This is actually the number of atoms it contains is going to be a mole. It's a package of those atoms, okay? A package of those molecules. So again, it's like saying you have a pack of a dozen eggs. But it's a much larger number than a dozen, okay? Because we have to work with large numbers of these. So if we were to say, for example, that we have one pack of eggs, a dozen eggs, that would be like saying 12 eggs, right? That would be the same thing. Is everybody okay with that concept so far? Okay. So if we have 2 dozen, then what would that be? 2 times 12, right? So 24. And we can keep going like that. If we have 10 dozen, it's 120, right? Okay, so if we have the weight of those, each egg equals 60 grams, then how many eggs are going to be present in a closed egg carton by weight? Well, we would take the 12, right? And then we would multiply that by the 60. Okay? And that would give us the mass of 12 eggs, wouldn't it? Okay. We're going to do the same thing here with moles. So if we have 12 grams of carbon-12, and it contains a number of atoms that we call a mole, then that's going to give us 12 grams of carbon is 1 mole, isn't it? Okay? Because this is, again, just like saying package. So 1 mole of any element has a molar mass in grams that's going to be numerically equal to the atomic mass of that element. We've played a trick. We've defined moles so that your periodic table, that number in the periodic table, that always gives you 2 things. It gives you atomic mass, and it gives you the grams for 1 mole. Nice, right? So we can have one number that actually represents 2 different things. And we don't have to make a super long periodic table. Okay. And so again, if we look on our periodic table, that is the atomic mass for those elements, right? That is also the molar mass for those elements, which is measured in grams per mole.
So what mole equals atomic mass of the element?
Huh?
What mole equals the atomic mass of the element?
Yeah. So if you only had one molecule, that would be an atomic mass units. If you have a mole of that element, that's grams. Okay. So the molar mass, again, is going to tell us the mass of 1 mole of a substance. It's going to correspond to the mass of a single atom in AMU. The number of atoms that's represented in 1 mole of a substance is 6.02, and that many zeros right there. It's long, isn't it? It's big. Okay? It's a very, very, very large number. This is referred to as Avogadro's number, and typically it's represented like this. So 6.02 times 10 to the 23rd, that right there is 1 mole of anything. Okay? So if you had that many pennies, that would be 1 mole of pennies. you had that many molecules, it would be 1 mole of molecules. Okay? Copper atoms, that would be 1 mole of copper atoms, right? Everybody okay with that? It's just like any other package, isn't it? Okay. All right, so again, that is Avogadro's number. Its symbol is capital N. Whenever you see that symbol, that's typically Avogadro's number that's referring to. This is again in honor of the Italian physicist Amedeo, I believe that is, Avogadro. I am terrible at many languages. And chemistry has a very long history, and so there's lots of languages that's been dying. So again, this is Avogadro's number. If this was in atoms, it's 6.02 times 10 to the 23rd atoms, and that's for 1 mole of those atoms. All right, is everybody okay with that concept? Fantastic. So again, if we look at this right here, this is carbon here, and we have here 1 mole of carbon. Notice that's not a huge amount of carbon, is it? No, it's just 12 grams, right? So that's just charcoal dust, and we have there coal dust, and that's 12 grams of it, and so that is 1 mole of carbon, or another way of saying that, you have 6.02 times 10 to the 23rd atoms of carbon, right? Okay. All right. So this right here is the conversion factor for Avogadro's number. All I'm doing here is I'm putting two truths together, aren't I? So 6.02 times 10 to the 23rd atoms would equal 1 mole of something. And so I put them both on the same side. That gives me a conversion factor, which is 6.02 times 10 to the 23rd atoms or molecules is to 1 mole, right? Divide by 1 mole. Okay, everybody good with conversion factors? If the conversion factor is true this way, if I flip it, what also has to be true? Exactly. So if I'm in, say, atoms and I want to get into moles, I can just flip this, can't I? All right, so the normal steps for converting, doing these problems, is step 1, we determine the unit on your final answer. Step 2, we establish the given information. Step 3 is deciding how to set up the problem. Step 4 would be solving the problem, and step 5 would be checking your answer. Does it make sense? Okay. If you have a huge number of moles, 10 to the 15th number of moles, does that make sense? Probably not, right? That'd be a huge amount. Okay. If I have a 5 atoms answer, does that make sense? Probably not, right? I'm probably not going to have 5 atoms or 5 molecules in something. I'm going to have like 10 to the 40th, right? Or 10 to the 20th, something like that. Okay? Now, I have really large numbers of molecules. Remember, the weight of a feather is not more than the weight of the planet. The weight of the sun is not less than the weight of a feather, right? Okay. And so logically, you can figure out if you're right or wrong on most of these problems just because you know objects, right? You know that you can lift the feather, you can't lift the planet, right? Okay. So molar mass and formula weight. The formula weight of a compound is going to be the sum of the atomic masses. The molar mass of a compound is numerically equal to the formula weight, and it just has units of grams per mole. These are related concepts. Formula weights are the same thing as a molecular mass or molar mass. The only difference is that molar masses are for covalent compounds. Formula weights are for ionic compounds. Okay? You do the same thing. If you want the formula weight or molecular mass of something, all you have to do is you go onto your periodic table, you add the numbers together. So for example, if we're trying to find the molar mass of a compound, CH4, we would go on our periodic table, we look at carbon, right? Carbon's a 12. We then add 4 hydrogens. Those are each 1, and so that would be 12 plus 4, which is 16, right? That would be 16 grams per mole. That's the molar mass for CH4. Now, just to make things a little bit confusing for no real reason, biologists have decided to name something that was already named AMU, Daltons. So a Dalton, which is abbreviated DA, which you may have seen in the biology courses, they typically use those a lot, is an AMU. They're the exact same thing. They're just used mainly in biochemistry and biology. And they're used to calculate weights of large compounds. Typically, they put them as kilodaltons, thousands of daltons. Okay? And there is no difference. They're AMUs. They just decided to name something that was already named something else 40 years after. So, can't tell you why. They did that. So this right here is your Lewis structure. This one's for methane. It's going to, when we write it on paper, like the Lewis structure is normally written, look flat like that, right? It is not actually flat in reality. It looks more like this. This is called tetrahedral, okay? And what you're seeing is that whenever a compound has these electrons that are contained in bonds, those electrons repel each other. They don't want to be close together, okay? And so they're going to separate out as far as they can get. If you were to take 4 balloons or 4 objects and tie them all together at a central point, what would happen to them? Would they all stay scrunched up on the top? No. They'd spread out as much as possible, right? And what you would see is if you attach 4 balloons together, you could try this out if you want. You can just clip together 4 balloons. They would actually separate out to this structure right here. Notice it looks like a camera tripod. Can you see that? Yeah. And that's because a camera tripod is doing that for the same reason. It wants to be as stable as possible. So it has 3 feet on the bottom right, maximum separation. And then it wants the camera to be as high as possible, and so maximum separation for the top coming up, right? So that's tetrahedral as well. It's a camera tripod. Everybody okay with that so far? Okay. Okay, again, that is referred to as tetrahedral. And that's because we have 4 things that are all trying to separate out as much as possible. So here we have the notation to represent that on a 2-dimensional paper. And this is called the wedge dash notation. So instead of just using flat bonds for everything, we can represent bonds coming out towards you and bonds going away from you with this notation. Okay? So the stuff that's just flat in the paper is still just a line. Everybody see those lines right there? So what you're seeing for these ones is those are flat in the plane of the paper. Okay? So these 3 are in that plane of your paper or screen. This one here, see how it looks like it's kind of fading away from you? With that dash notation. It looks kind of like you'd write it in a 3-dimensional drawing, right? And it's fading away. Okay. That right there is going behind the screen. It's going away from you. So that hydrogen is sticking out away from you, right? And then this one right here, see how it kind of is 3-dimensionally like it's coming out towards you, right? It's going to poke you. Okay? So this one here, the wedge here, is what it's referred to, is the one that comes out towards you. So that hydrogen's jutting out towards you and is coming out of the plane of the paper. Okay? Is that making sense so far? Can everybody kind of see it? See how it looks like the tetrahedral structure once you get used to it? Yeah. And there you go. That's how that's represented in a 2-dimensional plane, writing on paper or drawing it. So the model that predicts this sort of how these would look, this maximum separation, this is called valence shell electron pair repulsion model, or VESPR. Okay? And what it does is you take these are called electron domains. They're areas that have electron density in them. Okay? They want to repel each other as much as possible because they're all negative, aren't they? And so they're going to spread out as much as they can. If you have 4 objects, that's going to spread out in 4 different directions as much as possible, right? If you have 3 of these, it's going to separate into 3 directions. Maximum separation for 3 is a triangle, isn't it? Okay? And so this can allow you to predict these structures quite successfully, actually. And whenever we do this, we're always going to go ahead and take the central atom, typically represented with a capital A in the Vesper form. This is going to be, for example, carbon, and that one we just looked at, that's our center. Everything else is what we're going to look around are the center. Whenever you're trying to determine geometry, you always look at the center, don't you? Okay, so the next thing we need to determine is the number of electron. Your book refers to them as charge clouds. This terminology changes in every single book I've ever seen. Like, every single author is a little different. I've only seen 2 where it actually is the same out of 10 I've seen. Okay? And so this book says charge clouds around the central atom. I typically refer to them as domains because grammatically it's actually more accurate. Okay? But they're areas that are occupied by electrons. That's it. Right? Charge clouds, domains, electron domains, either one. Fine. Okay? So what you're going to have here is you'll have a central atom. You'll have areas those electrons occupy. They have negative charges. They're going to be repelling. The charge clouds that are in bonding are going to be called bonding clouds in your book. Okay? And they're electrons that are between 2 atoms because they're in a bond. The lone pairs are going to be non-bonding. And so those ones are non-bonding clouds in your book. And so they're going to be areas electrons occupy that don't have another atom on the other side. Okay? Okay. Next time around, I'm going to pick up here on this next one. You can see I'm running a bit behind on this, aren't I? Good thing I moved that test. Okay. Anybody have any questions? All right. You all have a wonderful day. I'll see you next time. Please try out the homeworks. Let me know if you have any issues.
You got my email with my doctor's note, right?
Yes, I did.
Okay, perfect.